Hey, welcome back to day 2 of me being gone. So this should be 5.2a, and you should be watching this on Thursday if you are all caught up. So today what we're going to be looking at is the behavior of power functions. So we're going to learn what power functions are and kind of some rules associated with those. Okay. Again, just like yesterday, please make sure that you are following along on the PowerPoint, which is on Canvas. You should be taking pauses to complete some problems on your own when I tell you to. All of this comes from your notes, so you should still have your notes out. And then at the end of class, you've got a DOL on Canvas, and your homework will also be on Canvas. Okay? So let's go ahead and look at our warm-up. Again, this is 5.2a. Go ahead and pause the video, take some time to do that warm-up, please. Okay, here we go, going over that warm-up. So the first question was to determine the volume of a cube with side lengths of 4. As we talked about yesterday, volume is length times width times height. Though for a cube, those are all the same, so it'll be 4 times 4 times 4. Which is 64. So the volume of our cube is 64. Question 1, write a function to find the volume of a cube with a side length of x. We just did that here, right? But it's a cube, so they're all the same. So our options for a function x times x times x, which we know is the same thing as x cubed, should be our function. 2, we're going to use this function to complete the table on the graph. So negative 2 times negative 2 times negative 2 is negative 8, negative 1, 0, 1, 8, and then 3 we didn't do yet. 3 times 3 times 3 again is 27. And we want to plot those points. That one's going to be off my graph just a little bit. There's just a lot of it. Way down there. Negative 1, 1, 0, 0, 1, 1, 2, 8. Again, that's way off, and that one was also way off. But we've got a general shape here, which is good, which is what we were looking for. Okay, and then 3, what portions of the graph make sense for this problem situation? We're talking about the volume of a cube, so how can you have a negative side length? That doesn't make any sense. So the portion that makes sense is everything in our first quadrant here. I'm just going to circle that in green. That part makes sense for our problem situation. Alright, let's go ahead and move forward into some notes on power functions. So your first blank there is a power function. A power function is a function of the form a, so any number out in front, x to n, where n is any non-negative integer. So non-negative meaning it's got to be positive, and integer meaning a whole number. So 1, 2, 3, anything like that. I did give you a bunch of examples. I gave you power functions 1 through 6. So we know 1 is a straight line. We know 2 is a parabola to the third power. There's that graph that we just got during our warm-up. And then we kind of see maybe there's a pattern developing here. So question 1a, down directly below that, says to sketch and label the next 2 graphs in the sequence. So what I mean by that is x to the 7th and x to the 8th. Go ahead and pause, take some time to do that. So x to the 7th power is going to look a lot like x to the 5th. Actually, that's probably really bad, because if we look at comparing x to the 3rd and x to the 5th, we see that it's actually getting flatter there, right? So my x to the 7th doesn't look great. we want it to get a little bit flatter as we approach the origin. Alright, and then that same thing is happening with with x to the 8. We know that's going to look a lot like x to the 6. If we look, pointy, flat, flatter. So this one's going to be even flatter than that. It's probably way more dramatic than it needed to be. Okay. 1b, stating any observations or patterns that we notice about the graphs in the sequence. So the first pattern that we noticed is parabola, squiggly, parabola, squiggly, right? That alternating pattern is going to keep happening. The other observation that we noticed is that it keeps flattening out. As we go higher, those keep getting flatter. Okay, let's go ahead and turn our page. To question 2. Question 2, A and B. Go ahead and try this one, then check with somebody around you for what they got. Based on what we did in that last problem, sketch x to the n when n is 12. So you're sketching x to the 12th power. And here you're sketching x to the 27th power. Go ahead and do that and then check with somebody around you. Make sure that we're in agreement there. Alright, let's go ahead and look at 2C and D together. I just want to do a for instance with you guys. So this is saying where n is 2m, where m is or an integer greater than 0. So an integer greater than 0 is going to be like 2. Okay, so if we plugged in 2 here, 2 times 2 would get us 4. So it would be graphing x to the 4th. Now we know what that's going to look like. But what if I used a different value? What if I used, say, 5? So we'd do 2 times 5, 10, x to the 10th. Let's try one more. What if I picked, I don't know, 7, get 14, x to the 14th. We should notice that all of these values are even, so they're all going to look like our even degreed power functions, like that. Now, sort of that same idea over here at D. So if I picked any value for m to b, so again we'll do 2, but then we've got this plus 1 at the end, which makes that not 4, but 5, so x to the 5th. If we plugged in 5, we'd get 11, this would be x to the 11th. And if we plugged in 7, we'd get 15, so x to the 15th. You should be noticing that all of those are odd, so they would look like our odd degreed power functions, something like that. Alright, next vocab word over here, the blank of a graph, and that one there is n behavior. N behavior of a graph or a function, that should be or, is the behavior of the graph as x approaches infinity and as x approaches negative infinity. Alright, so the example that I have in the PowerPoint for n behavior is here. So we're going to walk through that really fast and just how we write n behavior. So if you look at this graph here, if I was to write the n behavior, we're looking at just the n. So what's going on here doesn't matter at all. Okay? So the way that we write this is as x approaches, we'll just do with a little arrow. So as we go to the right, that's getting bigger numbers. So as we approach infinity, it looks like our graph is going up. That means that y is also approaching infinity. The second half of that is for this direction. as x approaches negative infinity, y is also going down, so it's approaching negative infinity. So we're going to do a bunch more examples of end behavior, but something to keep in mind is that the x always comes first, and you will always need two parts of it. There will always be two sides of your graph, a left and a right. Okay? We just need to look at what that graph is doing. Is it going up, down? Is it approaching some value? So that's the parts that we're going to have to look at there. So in that PowerPoint, there's also some checks for understanding just to see how you're doing. So the first one, to determine the end behavior of this graph. Go ahead and pause, give yourself some time to think about what the end behavior of this is going to be. I get listed all of our options over here. So the first question that you should be asking yourself is, what is the graph doing as x is getting bigger? As x is approaching infinity, what is the graph doing? Well, in this case, the graph is going up. And because it's going up, y is approaching infinity. We might need to do some test-taking strategies here. That means that this is still an option. This one is not an option. This one is not an option. And this one is still an option. So we just need to decide between 1 and 4 now. So the second question is, as x is getting smaller, as we're approaching negative infinity, which just means to the left. So as we're going to the left, what is the graph doing? Well, it's going down. So y is approaching negative infinity, which means our answer is number 1. Okay, we've got another one of those to do. Sliding this up a little bit. Second check for understanding. Go ahead and pause it to determine the end behavior. Again, remember that everything in the middle does not matter. Okay, we're only looking at the ends of our graph. So the first question we should be asking is, what happens as x is getting bigger? As x approaches infinity, as we go to the right, our graph is going up. That means that y is approaching infinity. So again, that takes away 2, and that takes away 3. Alright, second question. As we go to the left, as x is getting smaller, our graph is going up. So y is still approaching infinity. Y can approach the same thing in the same direction, that's fine. So as we go to the left, our graph is going up, which means we have an end behavior that looks like 4. So flip back over to your notes. We are going to identify end behaviors for different power functions based on the number in front. So let's go ahead and do the odd power function, odd degree power function, which again is going to look like this guy up here. And if a is greater than 0, that means it's positive, meaning it's going up at the end. So it's going to look exactly like this guy. So in your table, go ahead and draw that graph. Okay, and we're going to identify our end behavior. So as x approaches infinity, meaning as we go this way, our graph is going up. So y is approaching infinity. Second, as x approaches negative infinity, so as we go this way, looks like our graph is going down. So y is also approaching negative infinity. Now, this is the last one I'm going to do with you guys, and then you're going to pause to do the even degree power functions. This is still odd, so it's still going to have the same shape, but having a negative in front, having a less than 0, is just going to flip it over. So it's going to look like that. We're going to still start at looking at what happens as x approaches, as x approaches infinity, as we go that way. So as x approaches infinity, looks like our graph is going down. So y approaches negative infinity as well. And secondly, we're going to look at what happens when x approaches negative infinity as we go to the left. Looks like our graph is going up. So y is approaching infinity. Now I do want to make sure that we've got our graphs right when we go to do this. So the even degree power function is our regular parabola looking thing. And having that negative in front is just going to flip that over. So it's concave down. Go ahead and pause our video and come up with your end behaviors for these two graphs. Alright, let's go ahead and move forward. If you don't have a graphing calculator, now is the time to grab one, because we are going to graph these 4 even power functions on our calculators. We're going to do that really fast. There is a typo here that you guys need to change. It should say f of x equals g of x equals h equals 0. Okay, go ahead and grab your graphing calculator. Do this together. One second. Here we go. Okay, so in your y equals, clear anything out that we have there. We're going to do x squared. We're going to do x to the caret sign 4th and x to the 6th. In the PowerPoint I gave us specific windows that we want to be set at, so go to your window, and we're going to set our window to -4, 4, -4, 4, and go ahead and hit graph. Okay, so all the same parabolas we thought we saw before when we went over our power functions, but we can see a little bit more of that flattening out than we could see before. We can also see that there are some points that we have in common. If you guys would like to go to your table, you just go second table, and it will pull up your table for all 3 graphs. And I'm not so much concerned that your graphs are super duper perfect, so that's not a big deal. Let me pull up that table just so we can kind of see what's going on. When I go to graph this, my first one's going to be super easy because those are all the squareds. This one's to the 4th and the next one is to the 6th. So go ahead and plot some of your points for those 3 graphs. So the first one, I've got 0, 0, 1, 1, 2, 4, this guy we're used to seeing. Also, as we keep going negative, we see those values repeat. Okay, so that's my x squared. Go ahead and label that in your graph, or in your notes, just so we remember which is which. We can see for y2, which is our x to the 4th, we still have 0, 0, we still have 1, 1, 1, and we still have -1, 1. So these 3 points are still there. this one, and this one. But then when we get to 2 and negative 2, we get to 16 and 16. So over at 2, I'm going to be all the way up at 16, which is way, way, way off my paper. Like up there somewhere, and up there somewhere. So connecting those. There's that guy. Which means that x to the 6 is going to be even more off the paper. I'm sorry, that should be x to the 4th. Yeah, x to the 6, if we look at our table, huge numbers. Like at negative 2, when x is negative 2, we're already up at 64. But notice we still have negative 1, 1, 0, 0, and 1, negative 1. Okay, so I'm going to go ahead and graph those 3 points. And then I know that, yes, the next point is way off the graph, but that means it's getting steeper faster. And that's x to the 6. Over to the side here, it asks a few questions about those graphs. Let's go ahead and talk about the first one. It says, notice that all 3 graphs intersect at 0, 0 right here. Therefore, f of 0, this black graph, is at 0. G of 0, the green graph, is also at 0. And h of 0, the pink graph, is also equal to 0. There's another point where that happened. Actually, there's another 2 points. The first one is at negative 1 right here. So I'm going to use function notation to write that. So I'm going to write f of negative 1 is the same as g of negative 1, which is the same as h of negative 1, and all 3 of those graphs are up at 1. There's one more place where that happens. Please go ahead and pause the video and find the place where that happens. Next, we're going to answer our little sentence stem. It says, as the even degree power increases, as we go from 2 to 4 to 6, what's happening to our graph? You should be noticing 2 things. The first thing is that as it gets bigger, we get steeper. The graph gets steeper. Second thing we should be noticing is that it does flatten out. Okay, so as our numbers get bigger, or as our exponents get bigger, the graph flattens out in between negative 1 and 1. That's the next thing that we're going to talk about. So once you're done with that, go ahead and flip your notes over. We're going to talk about why does that happen. So 1D says to explain why the graphs of the even degree functions flatten out as the degrees increase between negative 1 and 1. I think the most obvious option here is just to pick a point that's there and see what happens numerically. So let's look at 0.5. And the 3 functions we were working with were x squared, x to the 4th, and x to the 6th. Now if we're plugging in 0.5 as our x value, if we do 0.5 times 0.5, right? Well, even if we don't know what that is in our brains, we've got calculators that will do that for us. So 0.5 times 0.5, 0.25. Notice that that's smaller than what we plugged in. For 1/4, if we do that same thing, for x to the 4th, if we do that same thing, we know we're doing 0.5 times 0.5 times 0.5, right? I'm going to write to the 4th, because it's the same thing. I can do 0.5 to the 4th. We get this way smaller number when we do that. 1/4 compared to 0.0625, right? And lastly, x to the 6 0.5 to the 6. We get an even smaller number. So the reason that our functions are flattening out when we get bigger is because when you multiply by a decimal, by something that's less than 1, or something that's between -1 and 1, right? The more times you multiply it, the smaller it gets. So not only do we have half of a half, we have half of a half of a half of a half, right? We keep cutting that in half, and that will keep happening as our degrees go higher. Okay. For E, explain why the graphs of greater even degree functions steepen when we exceed 1. Well, this one's a little bit easier to see. If we pick a number that's bigger than 1, even 3, right? Not that much bigger than 1. For x squared, 3 squared is going to get us 9. For x to the 4th, 3 to the 4th is going to get us 81. And lastly, x to the 6th, so 3 to the 6th, is going to get us, I don't know what, so I have to type that one in, 729. So kind of the opposite thing is happening here. The more times we multiply it, clearly it gets bigger. That's why it's getting steeper. So let's go ahead and take a look at our odd functions. Question 2, predict how the graphs of x to the 3rd, x to the 5th, and x to the 7th will compare to each other. So again, look for some similarities and differences. Go ahead and pause the video and make your prediction first. And then we're going to go ahead and do x to the 5th, and you're going to do x to the 7th on your own. I already gave us x to the 3rd right here. We also graphed this during our warm-up, so there's no need for us to do it again. When we talk about x to the 5th, I gave us some points. We're just going to put that to the 5th power. So 0 to the 5th power is still 0. Put my point at 0, 0. Next, if we do 0.5 to the 5th power, well, I don't know what that is, so I've got a calculator. 0.5 to the 5th power, 0.03125. I'm sorry, 0.03125. Put that in perspective for us, that's like 3 cents. If this is 1, we're up 3 cents. Okay, so if we are over at 0.5, we are not here. That's like a quarter, and we only have 3 cents. So we're going to be way down here. And then lastly, 1 to the 5th power, well, 1 times itself a bajillion times is still 1. So 1, 1. Now, before we can actually figure out what's going on up here, what happens as we keep multiplying by bigger numbers? This is going to get steeper just like before. So if we even did one more point, we would see that anything we go past 1 is going to get us up above this graph. So, like that. And that same, we're going to have a similar look to it, just in the other direction. So super close to our x-axis there. Crosses here and then gets steeper downwards. Go ahead and graph h of x, which is x to the 7th power, and then check your prediction, see how we did. Now before you guys actually go and do your DOLs, we've got a pre-DOL here that I want to make sure we talk about so that you will be more familiar with what's going to be on your DOL. Here is that pre-DOL. go ahead and pause the video now and try to answer this on your own. You can put it in your notes like at the summary page, or you can put it on a whiteboard. It doesn't matter to me, but try to do it on your own first and then watch for the answers. Okay? All right, question 1 wants us to describe the end behavior of the graph. So here's our graph. Again, your end behavior should have 2 parts to it. The first part is the positive, so as x approaches positive infinity, as we go this way, well, it looks like our graph is going down. So that means y is approaching negative infinity. It is going down. Alright, second question. Oh, my bad. We didn't finish that one. As we go to the left, as x approaches negative infinity, looks like our graph is going up. So y is approaching infinity. Should make my negative a little clearer there. Okay. Question number 2, describe the end behavior of the function x squared. X squared is just a regular old parabola. Looks like that. Both ends of this graph are going up. So we'll have as x approaches infinity, as we go to the right, our graph is going up. And as x goes to negative infinity, negative infinity, our graph is also going up, so y is approaching infinity. Third question, describe the end behavior of negative x to the 4th. So that looks a lot like this one, but we know that negative is going to flip it over, so it actually looks like this. As x approaches infinity, as it goes to the right, our graph is going down. So y is approaching negative infinity. And as x goes to negative infinity, as it goes to the left, our graph is also going down. So y is approaching negative infinity. On that last question, how do the graphs of x squared and x to the 4th compare? Well, again, we know 2 things are happening. Firstly, they are pretty much the same shape, right? They'll pretty much look like that. The other thing we should know is this one is going to be steeper past 1 and negative 1. Right, meaning these 2 ends, but it will also be flatter between negative 1 and 1. Alright, I think you guys are ready for DOL. This is 5.2a DOL. Once you are done with that, please work on your homework. And see you tomorrow for 5.2b.